Hi, good afternoon, everybody. My name is Nick. I'm a senior principal network engineer at Atlassian, the company responsible for every Jira ticket ever. So yeah, we make collaboration software, Jira, Confluence, Status Page, Trello, Bitbucket, and yeah. So basically, we've been doing a lot of stuff on top of AWS, and we've kind of built interesting things. So today I'm going to walk you through our journey into the AWS cloud, and we'll look at some of the requirements that were given to us, to the network team, and the solutions that we've come up to solve them. One of those solutions is about managing VPC peerings at scale. The other one is about building private Anycast inside of AWS. And the last one is about using direct connect gateways for fun and profit so that we can build some software backhauls between our sites using AWS network. So Atlassian is all about teams. We have a lot of teams. We believe in teams because we believe that people will do their best work, and when they're in a small autonomous team, where they're given the means and the autonomy to build whatever they need to build. That means that we end up with a lot of teams, and our mission is to unleash the potential in every team. So we've done that inside the company, and we try to do that outside of the company. And for the network team, that means that we end up with a lot of teams, which give us a lot of requirements. So what are those requirements? What do those teams want, and at what scale? Well, they're pretty simple. They want to connect to absolutely everything. They want an infinite amount of bandwidth. They want no latency between anything and anything. And they want it all for free. So that's pretty easy to build that, right, with AWS. At what scale do we need to deliver that? We have more than 100 accounts, probably getting to 200 these days. We have over 200 connected VPCs. We're present in 6 regions, probably 8 before the end of this financial year. And everything is connected with multiple 10 gigs. Today, we've got 12 times 10 gigs of direct connect going between AWS and the rest of our infrastructure. So what if we just try to deliver those things just using the normal AWS building blocks without, let's say, taking the naive approach, without engineering anything funny on top? Well, the problem we would have is that VPC peering would be a big part of creating the connectivity between all the things. A VPC peering is where you take one VPC, you connect it to another VPC, then you take static routes and you point them at the VPC peering so that they can talk to one another. So if you think of doing that for, let's say, between 10 and 100 VPCs across 6 regions, just managing those route tables is going to be a nightmare. Like, it's going to be impossible. And those route tables are also in like hundreds of accounts. We would have to hire a whole team just to do that if we wanted to do it just manually. Also, route tables have limits. 100 routes today is still the hard limit for route table size. Again, if you think of the number of VPCs we have, we would hit that limit. And if we need to check a few more routes to connect to on-prem infrastructure and a few other things, VPC endpoints, it's very easy for us to hit that 100 route limit. So if we wanted to do private Anycast, well, we wouldn't be able to, right? Like in AWS, you can't inject routes that overlap with things, so you wouldn't be able to do private DNS. Today, we use Route 53 for our DNS, but because we have all of those accounts, and we want to use, every account wants to use their own private hosted zones, we have to put a layer between Route 53 and the DNS service that we expose internally. So we have that proxy layer, and the way we want to expose that proxy layer is through Anycast, because that's what we did back when we had everything on premise. Now we want to port that into AWS. There is just no very easy way to do that natively. And also, we can't provide very generic cross-region private connectivity out of the box. What exists today to do those kind of things in AWS are cross-region VPC peerings, but because of the problems I explained earlier, we can't do that at the scale that we need to do. Also, I have a few concerns, like doing VPC peering within a data center or between AZs. I don't have any concerns doing that, knowing that there is plenty of capacity, a lot of ECMP going on in the background in AWS. But I'm a network engineer. I know how international links go. And I want my paths that go between one continent and another to be able to reconverge using routing. With VPC peering, the routes are static. If there is a problem with the VPC peering with the link, I can't reconverge to an alternate path, even if it exists, because there is no routing, so I can't do that. Also, the other classical solution for those kind of problems is what's it called, the transit VPC, right? Where you spin up some software routers like a CSR 1000V or something like that, and you start to connect your VPNs to all your VPCs. That works, but it's quite expensive, and it doesn't quite scale to multiple 10 gigs. It doesn't quite scale in the way we like. Also, the reconvergence is a little bit slow. Like VPN will basically fail BGP health checks and reconverge within 30 seconds. We typically try to be under a second for things to reconverge, because we actually use our global network to route some of the customer requests, right? Like if you have batch jobs, you can have reconvergence time that go way up, but if you're actually taking a customer request, taking it into a region and forwarding it to another region, you can't have 30-second reconvergence time whenever there is a network event. So 4 years ago, when we started our journey, where were we? We had 2 sites in the US, one close to US East 1, one close to US West 1. Still, most of the infrastructure was on-prem, about 80%. The basic business case for getting Direct Connect at the time was just backups. We were shipping the backups into Glacier through the Direct Connect, and just that business case already justified the Direct Connect, so they were kind of given to my team when we started, because we had that to play with. Between the 2 sites, we had private links like MPLS type circuits, 2 times 10 gigs, and all the traffic that was going between VPC at the time would just hairpin between 2 VPCs through the Direct Connect, because VPC peering wasn't even a thing at the time. It's also at the time that we realized that route table limit was a thing, because with AWS limit, a lot of time you don't read the documentation until you run up against the limit, and that's when you realize that something doesn't quite work anymore. So the Atlassian network was growing. We got to 100 prefix on our private network, and all of a sudden, some prefixes couldn't reach some VPCs, and we're like, huh? So at that time, we started advertising RFC 1918 summaries into each of our VPCs so that we lowered the route table usage. So then AWS announced VPC peering. Everybody wants VPC peering. VPC peering is awesome because it solves 2 of our problems. We get infinite bandwidth because we're not going through the Direct Connect anymore. We're not capped by that capacity. And we get near 0 latency because we stay within AWS within the region. But the problem is with VPC peering is handshaking is hard. You need to make a request, accept the request. Once the peering is up, do a route table on that, do a route on that side, do a route on that side. And the route table size is limited, as we already found out. So we need to get a little bit smarter about this. We're a software company, so let's write some software to do that. So our design guidelines was everything still needs to be routable, because that's what we started with. That's what our users want. We do security with security measures, so we do security groups and knuckles. We don't use routing for security. And we advertise the 3 RFC 1918 prefixes over the Direct Connect, so everything has to be reachable. And we don't want the VPC owners to have to manage the handshaking and the static routes and all of that. So we basically came up with the tool that creates the topology that we want. At first, we wanted to have just one full mesh in the region that connected all the VPCs to all the VPCs and basically would copy what we had with the hairpinning on Direct Connect. But because of route table size limit, we decided to go and create the concept of an environment where we say, all my prod VPCs actually need to talk to each other, but all my staging VPCs don't need to have the optimized path when talking to my prod VPCs. Everybody still falls back to Direct Connect and hairpinning if they need to, so connectivity is there, but I don't need the full mesh, and I can save on route table space. Those mesh can overlap. The same account, the same VPC can be in as many mesh as required. That's handled by the tool. A particular case, for example, here as well is, let's say we've got a VPC where we have a Cassandra cluster, and it's actually in a separate account. And we've given access to that account to a third party because they manage the Cassandra VPC for us. And that's a nice way to do separation of duties and so on, but we still want this VPC to be peered. We can create a special, like a custom environment just for them, and just put those two VPCs in them, and PRD still manages the VPC peering in the route table. Yeah, you can see in this example as well, so we've got some resource like an LDAP server or Docker repo. They need to be available from staging and from prod, so we put them in the multiple things. So we create a config file that describes the topology we want. We have actually switched to YAML so that it's a little bit more compact now, but this slide is still on the old version of JSON. So we kind of go through the regions first, so because we don't yet support in the tool cross-region VPC peering, that's on our to-do list of things to add. And under each region, we have a list of environments, so those are the different full mesh. And under each environment, we have a list of accounts. The same account may be in multiple environments, as we saw. And then you can see that a particular VPC can be in multiple accounts. That describes the entire topology. We have left one bit of the configuration that's left with the VPC owners because we don't actually know which route table does what within a VPC. So because public route tables, private route tables, they might have route tables for specific purpose. We tell them basically anything that you want PRD to touch, just tag it with PRD eligible equal true. And if a route table is tagged in that way, we will touch it and we will install all the routes that you want into it. So we still give some control to the VPC owners, but the topology is defined centrally through the tool. So how does the tool actually do its job? Well, conceptually, it's quite simple. We do describe, we walk through all the accounts, we do describe of all the VPC peerings and all the route tables based on our list described in our topology. We compute the current state, then we compute the desired state based on the config file, and then we get to work and we add and remove all the peerings that are required, and we retry because API request may fail, or we might hit a rate limit or something, so we just keep retrying, and same thing with the routes, we add until the topology is exactly the one we want. So what's the result? The management overhead is gone. We can basically create our topology, implement it without having to go and click and log into a bazillion different accounts and region. And the route table usage is minimized through the use of different environments for the things that actually need them most. One thing that we do to figure out which are the things that need those things most is that we just do flow monitoring on the direct connect. So on-prem on our core routers, we do flow monitoring, and we basically identify anything that hairpins on the direct connect. And we can see who are the large users of cross VPC traffic, and we can then pick those up and tell people, hey, you should join this PRD mesh so that your traffic gets optimized and it's basically faster. So now we still have connectivity to everything, and we practically have infinite bandwidth and no latency. So we've built this tool now that does a lot of management for route tables, and basically can touch AWS and manage all those things. Well, what else can we do with it? Turns out it's possible to do private Anycast in AWS using a lot of the same tooling. Just as a refresher, Anycast is a network routing technique where you advertise the exact same prefix from multiple locations. And you have a health check mechanism so that if a location becomes unhealthy or the service in one place becomes unhealthy, it signals the routing protocol to withdraw the routes pointing to it so that traffic can break away and go to the alternate next closest location. Anycast is used extensively by AWS. Your Route 53 public servers, they're always using Anycast. They're like the same IPs are advertised from a bunch of different edge POPs by AWS. On the private side, AWS also uses Anycast. The 169.254 addresses that give you your metadata endpoint, your DNS endpoint, your NTP endpoint, that's all private Anycast. but you can't do your own. AWS offers you services over Anycast, but you can't build your own, except that you can. It's very simple. You just have to build this. Because it's not so simple, I'll break it down. The key piece to making this work is the layout of the Anycast VPC subnet. So we actually have one Anycast VPC per AZ in each region where we want to make Anycast services available. And they all use the exact same CIDR range. In our case, we've used 10.53.0.0/16 so that we could have our DNS service anycasted over 10.53.53.53. The trick with that subnet layout is that we basically split it into the front-end subnet is actually the same one everywhere. But within the front-end subnet, there is part of the range that we make a convention that is also the same everywhere. That's where we have our virtual IPs, our VIPs, where we expose the service. But we have a little chunk, a /27, where that is globally unique, where that is only used by this particular instance of the Anycast VPC, and it's different in every instance of the Anycast VPC. And we use that so that we can health check a particular Anycast VPC and know that we're hitting that particular one. At the back end, the other half of the subnet, it's mostly unused. We just, again, we pick one subnet, a /25 there, that has just globally unique IPs. And there is no overlap at the back end, so that we can use that subnet to reach EC2 instances that are inside the Anycast VPC and have those instances talk back to backend services or whatever else they need to talk to. So I've got now my Anycast VPC I've drawn. Let's say that I've got 2 availability zones, just because if I had 3, it wouldn't fit on the slide anymore. And I've got client VPCs. They're also multi-AZ, just like everybody else. I've got VPC peering going between my client VPCs and my Anycast VPCs. But I don't have any routes yet. So the routes that I'm going to install with PRD as kind of static routes will target the health check subnets, and only those health check subnets. So this means that I can have a Lambda in my client VPC that I run on a schedule. And that Lambda will health check those health check VIPs, and it will report whether the health check is succeeding or failing back to a DynamoDB table. So now I've got a DynamoDB table that has records of the last time that my service was healthy in each of my AZ. And then I have another Lambda that runs outside of the VPC. And all it does is it queries the DynamoDB table, and it looks whether there was a success reported in the table for a particular AZ. And based on that, if there was a success, it installs the routes that point to the Anycast VIPs. It kind of works as a dead man switch, so that if there are no success reported in the last 5-10 seconds, I then withdraw the routes. So that basically, if all else fails, what happens is that all the Anycast VIP routes are withdrawn, and that means that my RFC 1918 summaries pointing to Direct Connect take over, and I automatically fail over to an alternate region. So if my service in the region is totally dead, it just uses Direct Connect, go to a different region. From inside the Anycast VPC, I've got proxy instances that pick up the traffic on the VIPs and on the health check and proxy it to the services that I'm actually fronting. There, again, the EC2 instance, we use a proxy called VTM, and it health checks the backends, and it can fail over to the alternate AZ if it needs to. And if all fails, then it just it stops serving, which triggers the Lambda, which triggers the failover to the alternate region. So with Anycast in AWS, we just create an insane amount of redundancy, and that means that we can expose services where basically putting it behind an ELB is not an option. So UDP-based services such as DNS, obviously you can't use DNS to expose DNS. Things also like syslog endpoint, statsd endpoint, where your client may actually only resolve the IP address of the syslog endpoint or statsd endpoint at start. And then if you put that behind an ELB, the ELB changes IP and it doesn't work. There are a few things, mainly DNS, but a few other things that can really benefit from using Anycast. You can also actually use this to fan out. If you have a service that needs to be presented on a single IP, but you want to fan it out to a lot of instances, you can't necessarily do that with ELB. Here you can have one per AZ. You could even split out your route tables further if you wanted to, and you can have something that looks like one IP and is actually served by as many EC2 instances as you want. So we've created a lot of resiliency. The health check at the front end, the health check at the back end, the failover to the alternate region. And normally, we have preference so that you stay within the same AZ. The client VPC will target the Anycast VIP in the same AZ, which will target the backend instance in the same AZ. So even though we cross two VPC peering, we stay in the same AZ, so we're still talking about less than 1 millisecond to typically have a request go through. All right, so we've talked about keeping latency low, having infinite bandwidth. What we haven't talked about yet is getting free stuff. We need to get some free stuff, especially from Amazon. Does anybody know, as far as network transit cost, what network transit cost do you get for free in AWS? I'm sure somebody needed it. This is not as intimate as I hoped to get some response from the audience. So you may know that when you send data into AWS, it's always free. It's when you pull data out that they typically charge you, but to send data into AWS via Direct Connect or Internet, it's always free. So we're going to try to play a little bit of a trick on this, to use Direct Connect Gateway to take advantage of that and get some free stuff. So another quick poll, maybe a show of hands might get a little bit more. Who has Direct Connect here in Australia? Yeah, I would say about half the people. Who has a Direct Connect also outside of Australia? Not too many. I was kind of expecting that. We were lucky that we do. Who has private circuits going between different sites that you manage within Australia or outside? Yeah. So based on that, you may be interested to know that Direct Connect Gateway can be used to get some free stuff. So Direct Connect Gateway is a service where you can now have a Direct connect from where it physically is to a VPC in any region. So that means we can build a topology like this where I've got a Direct Connect POP in US West 2 and one in AP Southeast 2, and VPCs on either side, and my Direct Connects are actually cross-connected to both. In the VPCs, I run a regular EC2 instance. I just make sure that it's an ENA-enabled ones because they've got better network characteristics. And I can run a software BGP router on there, such as Bird. So once I've got that, what do? I build some GRE tunnels between my on-prem routers and the Bird instances on each side. So I've got tunnels. I can run BGP on top, and now I just do a little bit of BGP traffic engineering so that, because I've got two paths to go between my core router in Sydney and my core router in Oregon. So the path that I'm going to select is the one that always goes into AWS as much as possible. So to cross the Pacific Ocean, I go straight to US West 2 using Direct Connect Gateway, and that's free. I get out of US West 2 to my core router in Oregon, and that's, I mean, I pay for that, but that's local Direct Connect cost. And for the return traffic, again, I go up to my instance in AP Southeast 2 and go back down at the local cost. What that means is that I've got a bidirectional BGP link between the two continents, and I never pay anything when crossing the Pacific Ocean, which if you talk to any circuit provider, they're not going to agree to give you that. So, I mean, I'm saying it's free. It's not totally free. What does it mean? If I run one of those, in reality, we've been running this in production for a few months, and obviously we run two of those. But if you run a single one of those, you need one instance on each side. That's about $200 a month. And your per gig cost for the traffic is 2 cents when you go from Sydney to Oregon and 4 cents when you go from Oregon to Sydney, just the local Direct Connect cost. How much traffic can you push through one of those? About 1.5 gigs is what I could get with an iPerf on either direction. The thing is, you can scale that horizontally. Right? There is nothing preventing you from doing more GRE tunnels. You're just capped by your capacity on Direct Connect and your core routers and their ability to do GRE. I'm assuming that the Direct Connects are sunk cost and that the control plane overheads are pretty negligible, which in practice they are. So yeah, that has worked for us. The good thing is you can really get generic connectivity. So our office in Sydney, our few offices in Sydney, are all connected to our cores that are in a Sydney data center that is connected via AWS Direct Connect. So for the past few months, everybody that connects to any VPC in the US from the office in Sydney is going through that. We've had a bunch of flops and things, but because I've got BGP and I can reconverge, nobody has ever complained about any outage. It's been working quite well. So what was the result when we run this? Cross-region is free. We finally got free stuff. The connectivity is completely generic, right? We're talking about doing BGP between on-prem and on-prem. I don't have to worry about route table size in any way, shape, or form. And my scaling is not too limited. Turns out if you take Direct Connect Gateway, ENA, which is the enhanced network adapter, so the good networking for EC2 instance, which you get on C5s and R4 and a few other. You add GRE and BGP, and you mix it up, you get your triple G bandwidth expander. So that's what it's called. So we finally got free stuff. All right, so what did we talk about today? How we can use PRD to solve the management and scaling issues that we have for VPC peering. We really got to get to open sourcing this. When it's going to be on bitbucket.org/Atlassian, and we're going to put the code there. We need to do a little bit of cleanup, and it's been on our backlog for a while, but we'll definitely get to it. If you add some extra Lambda health checks and proxies in DynamoDB, you can actually simulate private Anycast inside of AWS. And then on the side, if you want to connect and use AWS and get a bit of free stuff to get your global network going, you can do that between your direct connected POP using the G3 bandwidth expander. Thank you very much. I'm happy. I thought that it was going to be a smaller room and that we're going to be able to have more of a conversation, but I'm more than happy to take questions here at the front if you have any. Thank you.